Okay, I think I'm done talking about the leapfrogging model, and I can go back and talk about estimation of the directional games in general again. Okay, so this is where we are. We talked about collusion in Australia. We experimented with the model. Hopefully you'll remember that. Then we talked about how to solve, how to generalize the backwards induction, right? If you have directionality of transitions through the state space. Then we talked about how to enumerate all solutions in these models with directionality. And that would lead us to the full solution of the leapfrogging game and, proving some theoretical results about the leapfrogging model. Now, let me talk about structural estimation of this. The idea that I will start with is kind of labeled nested recursive lexicographical search. And this is going to be another example of a nested estimator. So what we want to do is a maximum likelihood estimator with full solution on the inner loop. That's the general idea. Now, I think I've just convinced you, or well, gave you a little preview how hard it is to solve for all equilibria on the inner loop. And fortunately, you don't have to do that. In fact, there turns out to be a wonderful algorithm that simplifies that problem considerably if we break it out into these two steps. Okay, let's start with the data. The data is going to come from M independent markets in T periods, so that's quite standard. For now, I'm going to assume that all of the markets are playing the same equilibrium at the true value of the parameter. We can relax that later, maybe not today. At the true value of the parameter, or at any value of the parameters, there's going to be a set of equilibria that we will denote this E, okay, curly E. This curly E is really dependent on theta, right? As we just saw in the movies, for different values of the parameters, the set of equilibria is going to change. Now, we want to maximize likelihood, but we will separate this problem into two steps. On the outer loop, we will just consider the theta parameter, the structural parameter of the model. And that's going to be our maximum likelihood estimator, just the argmax of the likelihood. But on the inner loop, we will look at the likelihood computed at a particular equilibrium and maximize that on the set of equilibria corresponding to the theta that comes from the outer loop. Okay, that's the idea. Now, it turns out that this problem of maximization of a likelihood function on a finite set, that's where this wonderful algorithm can be applied. Before I go into this, let me talk about the reformulation of the likelihood function on the state space of the model. So what is this likelihood of a particular data, in a particular equilibrium? We want to sum up the logs of the choice probabilities of the actions that we observe in the data at particular points in the state space, conditional on structural parameter. And this is implicitly also conditional on the equilibrium K. Which is a big, right? That's why we have this P super K in the likelihood function. These are the choice probabilities that come out of a particular likelihood. And now we are summing over markets, time periods, and players. And this should be M, I understand. Yeah, markets are there are suddenly N markets. Then anyway. Now, yeah, question.
So unlike Bertle's nested fixed point, you don't care about trying to recover the particular equilibrium that's played?
Oh yeah, I am.
You are?
So if you put these two together, what it says here is that I'm maximizing with respect to structural parameter and in the same time with respect to equilibrium. So we are calculating the likelihood. We are maximizing the likelihood subject to, or with respect to the structural parameter theta, and this additional parameter, which you can think of as a discrete parameter that selects an equilibrium. And this is very similar to what Stefan was talking about when he was talking about grouped fixed effects. Remember, there was this collection of discrete parameters which gave the assignment to the groups. You can think of this as a discrete parameter with respect to which we are maximizing the likelihood. Okay, back to this. I will set up the model in such a way that the data that I observe is actually within the boundaries of the model, right? So I want to solve the model to give me these choice probabilities at particular points in the state space with particular actions. So essentially, I can think of the data as you know, leaving on the state space. There's no unobserved heterogeneity here. And therefore, the idea is to just count the number of observations of my that I have in the data in a particular point in the state space. And the number of actions made, of a particular action made in that point in the state space. Is that clear? So due to the absence of unobserved heterogeneity, I can just transfer all my data into counts on different points in the state space. And that means that we can rewrite the likelihood in the completely equivalent way as the number of times that you observe action AI times the log choice probability for action action I in that point of the state space, which I now index with iota. So x iota is a particular point in the state space. And now we have to sum up over the whole state space, all of the players and all of the actions. Yep.
The unobserved heterogeneity just integrate first over the
Yeah, and have another outer loop over the unobserved heterogeneity. Yeah, we could do that. I think we could. No. Not yet. We don't need it. So we can allow for different thetas. Okay, well, I mean, the way that it's written, it actually does assume the single equilibrium. We have to write it in a much more complicated way, right, to allow for. But in principle, we don't have to assume single equilibrium in the data. Exactly. So essentially, this is going to go into Beaumont-Manresa type of setup where the played equilibrium can be completely free by market. This is a lot of computation. The BLM is a much more promising approach because if we can separate markets into groups and then they say each group plays the same equilibrium, that's much more computationally tractable. Okay, let's talk about that. Okay, but let me show you the algorithm. So now this is my state space, and on the horizontal, from now on, we will just basically put the points in the state space while keeping that dependent structure, the directionality that we talked about, right? So we start here with the point which is independent. This is our absorbing state. 0, 0, 0 means that the state of the art is 0 and the firms already reached that state of the art marginal utility of production. And the apex of the pyramid will be here, and the solution will in this end of the axis will depend on the solutions in the points which come before it. I can calculate CCPs from the data. That's what's on the top here. This is all simulated data today and so far. These are my counts of observations in different points in the data set. And this blue and red bars, these are the counts of firms making one or the other action. Okay. All right, so here's the key to being able to solve it without solving full equilibria. The method is called branch and bound, published in Econometric in 1960. Improved since then, and we still have space to explore what computer scientists have done with this. But it's essentially created for solving discrete programming problems and fits, minimizing, maximizing functions of a discrete set. Let me give you a little bit of theory and a feel of what it does, and then apply it to our estimation problem. So the idea is that you may have a tree of subdivisions of the set of admissible plans. Now, these admissible plans will include these integer values, right? But it's still possible to subdivide this big set of admissible axes, discrete axes, in such a way that you can specify a bounding function which is there to represent the best attainable objective on any given subset. Okay, so it has to have this monotonicity property. The bounding function has to be weakly decreasing in the cardinality of the subset. This is a mapping from the set of subsets into real numbers. This is for the max problem. And also it has to equal the criterion function if you evaluate it at the singleton. So essentially, if you can subdivide your problem into regions, or the set of all possible solutions into regions, and you have that function that tells you, that a particular region is promising or not promising, that allows you to skip looking at the regions which are not promising from the point of view of this bounding function. Right? And this is what it says over here in point 3. Yeah, we're not looking at the extensions yet, but maybe at some point. Here's a very simple problem, generic problem that can be solved by branch and bound. So imagine that I'm maximizing some f of x on the discrete set omega. F of x is an objective function from Rn to R. So we're thinking that this is a subset of Rn. We want to talk about these partitions, the curly Pj, into Kj plus 1 subsets, such that the first level basically has the whole set. Okay, so this partition curly P0 of omega is just it by itself. And then as this index j, as this index j decreases, then you have more and more of these partitions which are mutually exclusive subsets of the original omega. Right, so that's what we are looking for. We're looking for a sequence of gradually refined partitions, such that as you kind of go deeper in this structure, then you have more and more subsets in which you subdivide the previous subsets. And that's what basically these two lines define. Let me just show you a picture. So here's your full set of possible axes. You can subdivide it into, say, 3 on the first level, and this would be j equals 1. And then on the second level, you subdivide each of those, and so forth. And in the end, you would have subdivision into just single elements of the original admissible set. Okay? And here's the monotonicity that we require. So this bounding function, that's a function from the set of subsets, right? To R. At the singleton, it just has to have the same value as f of x. But evaluated at different subsets, it declines as you go deeper into this structure that I showed here. Okay, it's kind of abstract right now. Let me take it to the example. You can think of this as, this is a maximization problem. As we go all the way deep to the singletons, to elements which have only one point, then this function becomes the objective function. But for any levels above, this is like an approximation, right? It's an upper bound on the function that is the objective. How does it apply to our problem? We already have a tree. That's the RLS tree. That's the tree that we traverse to calculate all possible MPE equilibria. The bounding function is the following. Imagine that I calculate likelihood not of all the data, but only of the data where I have solved the problem. So think of this picture. This is where I start solving for equilibria, right? This is where the RLS tree begins. This is the absorbing state, easy to solve, and will produce certain choice probabilities for this particular point in the state space. I can already calculate the partial likelihood by using only the data that lives here. And as I traverse the tree and calculate more and more of the points in the state space, I can calculate the likelihood up to the point which is solved. Okay, that's the idea. Yeah.
So like, if you think of it as working backwards as you did before, but then your equilibrium selection mechanism is
going to be informed by the likelihood. Yeah, exactly. Now, does it have monotonicity property? So as I include more points in the data in the state space, I'm calculating likelihood of additional data. It will decline, right? As I include all of the data, as I go all the way through the tree to the last point, I'm getting exactly the likelihood that I'm trying to maximize. So I have this function that declines and is exactly equal to the objective as you go all the way through. And that's exactly what we need. But it's not all of it, right? So this is nice, but it's not enough. But let me start with this. How does it work? So remember, I'm solving the game. We solved the absorbing state and then the states that depend on that, the states that depend on that. And there's single equilibrium everywhere here. And I can calculate the partial likelihood only on the data that lives on these points in the state space. And imagine it's minus 3.2. Numbers are completely made up. And then there's the branching. So at this stage number 9, there are 3 solutions. I can plug in each of those solutions into the partial likelihood and get a feeling, which equilibrium seems to be more likely in the data. Okay, maybe that one. And I can apply this greedy approach and continue to traverse into that branch and do exactly the same thing every time the tree branches. And as I get all the way through, remember the path from the root of the tree all the way to the leaf is the Markov perfect equilibrium in the game, right? That's the combination of the value functions and the choice probabilities. And I've calculated partial likelihood all the way through. This now includes all of the data. And so this record, this is an actual likelihood of this particular equilibrium. And now I'm continuing to do the tree traversal as before. But this time, I'm comparing this minus 11.2 to this minus 10.1. Is it worth exploring this branch? The partial likelihood is already minus 10.1, but it's still above than this value, right? So maximum could still live here. So okay, let's explore that one, and boom, we got a new record. Now I'm coming back and I'm traversing this branch. Is it worth exploring this branch? It's not, right? Because we know that this partial likelihood can only decrease due to monotonicity. And it's already minus 13.7. It's worse than what we had. And so I will not explore this branch. I just say, okay, I'm done here. What about this branch? This equilibrium seems to be so unlikely that already in this point of the state space, it is less likely than the full equilibrium I already explored. So I'm not going to explore this branch. Oh, pressing the wrong button. And that continues, and I'm not exploring any of these branches here. But maybe there's a possibility that some other branch is still promising, right? I will continue to explore that branch and expand and calculate the equilibrium and all of these points that stem from this equilibrium on the stage number 9. And at some point, I may actually come up through this set of equilibria to something that looks even more likely. Okay? The idea is that in the same time, I'm not expanding a lot of branches, but in the same time, I'm finding exact maximum with this branching bound algorithm. So yeah, people in the 60s had small computers, but were very smart in coming up with ways to avoid computation. And that continues to the whole branch, so through the whole tree, and gives me exactly the maximum over the set of equilibria that I was looking for. So there would be a better and worse order. You would want to put data as close to the root as possible. And there is some flexibility to reorganize the order within the stages as we were dividing this state space into stages. And then taking a greedy strategy on each particular branching is not a bad idea. But because you traverse the whole tree in the end, you will always find the global maximum. So, and then of course, everything depends on how informative the data is. Because that's the data which lives somewhere in these points that gives you the partial likelihood values and allows you to skip computation. Now, are there any questions about branch and bound? Yeah.
So like what you find is guaranteed to be equilibrium?
Oh yeah, absolutely. So remember, we were traversing this tree to find all equilibria, and we've proven that if we can solve a small problem, then they're all equilibria here.
You're not doing like the Cartesian product like every possible way back. You're only traveling.
Oh no, you don't have to.
Yeah.
Right? I mean, on the previous lecture, we were traversing the same tree, but we were interested in the set of all solutions. Now we can inform ourselves where not to go. And we don't want to go there because we are now interested in maximum likelihood. Now, next step. So this branch and bound is great. And I don't know, we had the idea, then we tested it, and it was not great enough, okay? It allows you to skip calculation of equilibria, but not in the, it still like takes a lot of time. It doesn't cut out a lot of computations in the simulation. Here's the next iteration of the idea. Let's talk about the non-parametric likelihood. Now, I will calculate it, I want to make it as a function of any subset of points in the state space. And this is the same form as the likelihood, right? This is going to be summed up over a subset of points. And I'm going to use frequency estimator instead of the probability, which is computed by the model. This can be done for any points in the state space once I have the data, right? I don't have to solve the model to calculate this. It only depends on the counts from the data. Now, from Gibbs inequality, you can show algebraically that this thing here is going to be always greater or equal, maybe, than the true likelihood calculated at the same set of points. So the idea is now that for the bounding function, I was using the partial likelihood, right? I was using the likelihood which was computed for a given equilibrium K on a subset of points where we solved the model already. Now I can add this part for the points where we have not yet solved the model. And now my bounding function will contain a little bit of the actual likelihood, but the rest will be just this kind of optimistic bound. Optimistic in the sense that no parametric model can do better. And now look what happens. I'm now showing you yet another different graph. This is still the state space, ordered in the same way. These gray bars are counts of data. So this is where my data is. And now on the vertical axis, this is partial likelihood, essentially. When we don't have any data, we start over here. Well, we start in this absorbing point. This is my partial likelihood from just a single point. And as I go and solve the model on different points of the state space, each of these black lines corresponds to the partial likelihood of the equilibria which are solved on this part of the space. Okay, there are many lines because there are many equilibria, and because of this tree structure of equilibria, these lines are also branching a little bit. And so this, all these black lines represent the computations that you would have to do in order to calculate likelihood for all equilibria. Okay, that's like the maximum amount of work. I traverse the tree everywhere, don't pay attention to the partial likelihood, to this branching and bounding function. And if I've done that and then just took the maximum likelihood of the full data set, which is right over there, this is the point at which I've included all of the data. Then my maximum likelihood is here. And I can kind of trace it back you know, this red line represents the maximum likelihood line. And you can see that, you know, just taking the maximum, just doing the greedy strategy and then being done with it, it's not cutting it, right? Because over here, the data was, I mean, for the subset of data up to here, the equilibrium, which is actually maximum, you know, most likely, did not look like most likely over here, right? So the red line is not an upper envelope of this whole collection. We have to do branch and bound, right? We have to do the work to find the actual maximum. That's one thing. And what are the blue lines? Well, the blue line over there, that's the non-parametric likelihood calculated in the same way for kind of the subsets of data. Starts over here for just this data. And then as we add more data, it also declines, but has this flat spots where maybe everybody is is taking the same choice. And therefore, we don't get much information from these frequencies. But as I was saying, this blue line is always above any of the black lines. Okay? The idea now is this. I solve the model on this subset of points in the state space. I have the partial likelihood somewhere here, right? Part of the black line. Now I'm going to take the continuation kind of value, part of that blue line, attach it over here to partially computed partial equilibrium. And that blue line is going to give me kind of the optimistic projection of where the full likelihood may be. Does it make sense? So I'm going to combine partial likelihood computed on the data with the model, with the choice probabilities from a particular equilibrium, with the rest of the data being used only in terms of frequency estimators. And so if we do that, and if somehow we knew which equilibrium has maximum likelihood over here, and I just parallelly move that blue line to match it over here, this amount of computations under the blue line here is what I may hope to not do, right? Because I'm using the blue line to continue my partial likelihood all the time. So if I knew the red line right from the start, then I would never have to go into this region here, okay, into this region here. Is it clear? Yeah.
Data point start to do that because I'm thinking if we just do that too early, then maybe just rule out all these kind of possible likelihoods.
Yeah. So the question is, right? If I just computed a little bit and then use this line, and that would be still above, yeah, that means that I continue to explore. I'm trying to maximize, right? So if my projection falls above the current record, that means that there is still hope that as I add all of the data, I will still be above.
So this bound is computed on an as-needed basis. So like
this blue line is just pre-computed.
pre-computed.
Yeah, I mean, it only depends on the counts. And so you essentially you pre-compute it for the rest of the state space at each point.
You have to calculate it for all of the partitions.
So partitions here, yeah, you do, but this is this does not depend on the equilibrium, and that means that the tree is trivial, right? It's like one line. There is no branching for this line. It's the same for everybody. Okay, if this idea is clear, then let's think about what happens as the sample size increases. Because, okay, this is my optimistic cut down of the computations here. But then as sample size increases, my blue line, the non-parametric likelihood, is going to approach the parametric likelihood, at least if the model is well specified and we are close to the true parameter. And so it will be closer and closer to the red line. And that means that as I shift it over here, I'm cutting out more and more of the computations. The sharpness of this bounding function increases with the sample size. At the truth. at the truth. We'll see in Monte Carlo. But at least that's the potential, right? The promise is that if you have informative data and if you're not too far from the truth, then there is a potential that you don't have to do this heavy computation of enumerating equilibria. Essentially, this becomes really informative in which parts of that RLS tree you don't even need to go to. And then you're cutting out a lot of subtrees. So that's a comparison, right? So we're now with the larger sample size, we're cutting out most of the computation in the solution of the model.
What are the dark lines? So they are when there is a change in technology, but then they're also in between.
These lines here? Also, the vertical dark lines, good question. That's the division in the state space into the interior points. So this is going to be the apex, the interior points, the edge points, and the corner at different levels of the technology. I mean, everything can be read from these three numbers. So this over here is 444. There are 4 points in the simulation. Yeah. All right, so what do we have? We have that for any amount of data, the non-parametric likelihood is greater or equal to the parametric likelihood algebraically. Branching bound augmented with this non-parametric likelihood bound is really powerful in reducing the amount of computations. So with more data, and we're thinking about the number of markets, the non-parametric log likelihood converges to the true likelihood at the true parameter. And that means that that band where you have to do calculations becomes narrower and narrower. But in the same time, we're computing MLE every time. It's just that the amount of computations now depends on the sample size. So you improve numerical efficiency of the estimator, while the statistical efficiency, well, also improves. But it's MLE. Okay, what did you learn? Algorithms are important. If you want to tackle really hard problems, look around for maybe there's an algorithm that fits it better than off the bookshelf methods. I think that's the kind of the global message from this. And of course, if you have this integer maximization problem, look it up. What's the branching bounds, and maybe learn a little bit about that. I'm ready to give it to Bertel now to talk about Monte Carlo simulations. Okay.
I need the microphone.
This is the camera. There you go.
Oh, it works. Okay, so why don't we try this out? Try to simulate some data from this leapfrogging model estimated using a variety of different methods. So I just want to introduce some compact notation here for the primitives that we've been looking at. So the Markov-perfect equilibrium is the solution to both the Bellman equations and the Bayesian-Nash equilibrium equations. I know we have seen versions of this as many more Greek letters, but really it's just a mapping of value functions and choice probabilities on the right-hand side of the Bellman equation to value functions. Okay, so this is just a Bellman equation, and this is essentially our Lecture form. Okay, so you impose these mutual best responses by putting this into the Lecture form. Okay, so the set of Markov-perfect equilibria is these vectors of conditional choice probabilities and value functions that satisfies these constraints. Okay, so that's the Markov-perfect equilibria, and as Fedor showed, there can be quite many of them in these dynamic games. So this is a Bellman operator, this is the choice probabilities, and then sometimes we make the mapping from conditional choice probabilities to the value functions through the Hodge-Miller inversion. We call that gamma. Okay, that's going to be useful for introducing these different Other estimators in a more compact way. Okay, so we already talked, this morning about different ways to do structural estimation of games in static setting. Very much the same here. Okay, so there's these two-step estimators. They're fast. They're potentially there are some problems with estimating very high-dimensional conditional choice probabilities if you have many states and many players. But we can still estimate these conditional choice probabilities from the data, which is what you do in the first step. And once you got that, you already know what the values are, and you know what equilibrium was played in the data, at least if you're willing to assume that that equilibrium was the one played in the data. Okay, so once you got essentially pinned down what the p's are, you know what the values are and the conditional choice probabilities, and you can use that as a sample in the sample criterion that you use in estimation. For example, like minimum, like using method moments or minimum distance, or like here, or pseudo maximum likelihood. Essentially, you just put the best response function fixed at those estimated CCPs right into those likelihood functions. Okay, so you would just keep those conditional choice probabilities that indexes believes of the different players fixed at the data. Okay, so that's pretty simple. You maximize this over only over the structural parameters. Nothing looking for like chasing different equilibria and figure out what fits the most. We just pick the one played in the data. And then there's another pseudo likelihood we talked about in the model. It's kind of this recursive idea of updating these conditional choice probabilities by doing, you do first a two-step estimator, get your conditional choice probabilities, or estimate the structural parameters using the two-step estimator. That implies a new set of conditional choice probabilities. Then you can use that for indexing the best response mapping again, and then you do the whole thing again and estimate new set of conditional choice, new set of structural parameters. You get like a sequence of estimates. That is shown to be kind of from time to time can be a little bit unstable. And the problem, really the problem is that this best response mapping that you use inside the pseudo maximum likelihood estimator, that creates a new mapping they call the NPL mapping, which is not a contraction. So if you just continue to do successive approximations on that, you're not sure to converge to a single fixed point. Okay? Sometimes it converges, but you cannot be sure it's the equilibrium that was played in the data, and sometimes the cure can be a little bit worse than the disease. Anyway, so that's what Iskhakov is doing. Of course, if you start with very good guesses or very good estimates of conditional choice probabilities, it's going to be more stable, that mapping. Okay, we also talked about MPAC this morning, which is kind of a little bit different. Well, you maximize the likelihood, not only over the structural parameters, but now also over the whole set of conditional choice probabilities. That's conditional choice probabilities for all the different players and actions and states. Okay, so now it's not just a scalar like we had before for two players. It's like it's a whole vector, right? So that's potentially a much bigger variable to maximize over, and then the corresponding value functions. This is a way that Iskhakov and Su did in 2015 in QE. They maximize the likelihood subject to each of these two sets of constraints, like both the Bellman equations and the Bayesian-Nash equilibrium constraints. So they had like these two sets of constraints. We're going to try to actually implement another version of MPAC to reduce the number of variables by using the Hartz-Miller inversion. So you can combine essentially these two equations to one mapping from conditional choice probabilities to conditional choice probabilities. Then there's fewer constraints. Of course, they are harder to evaluate, but we are searching over a much reduced space, and we know those conditional choice probabilities. We can measure them accurately in the data where we have good data, so maybe there's more hope. So we want to compare with that other version of MPAC. So that's kind of estimator number 2. Okay. And then, of course, we do RLS. And so here are some Here are some key findings. I would say, it's robust, and I hope Fedor convince you. It's a computational feasible estimator, especially when we have lots of data, because we can knock out all those, very unlikely equilibria just from using the non-parametric likelihood as a bounding function. And then it relies on an algorithm that provably finds all macro-perfect equilibria. Okay, it may take time, but at least for a given set of parameters, we can always calculate the likelihood. Okay, we don't have to worry about solving for it using like iterative methods. And then it applies this branch and bound. Okay, so we would say this is fully robust to multiplicity of equilibria. It could still have the same problems with, remember I was showing the likelihood function would have all these kinks and discontinuities, and you can't run away from those. They're still going to be there. So we are working on relaxing the single equilibrium in the data assumption, and anyway, so why don't we just look at it? So I'm going to start simple. Okay, so I'm going to start with a single equilibrium in the model. Okay, so we have a model where there's only one equilibrium no matter what the parameters are. Okay, so simple case. Everybody should be able to do this, or all these different estimators should at least be able to do that, right? And then also, obviously also only one equilibrium in the data. It would be kind of weird if the model had one equilibrium, and all of a sudden it can simulate different equilibria in the data if we're using the model. Okay, so one equilibrium in both cases. So we're going to start with that, and then we're going to add multiplicity of equilibria in the model, and then allow that same equilibrium to be played in the data. And then we look at multiple equilibria in the model and multiple equilibria in the data. And so that's kind of work in progress, let's say in that way. Okay, but I'm 100% confident we can do it. It's just about how we group different categories of observations into different types of markets, for example, allow different equilibria to be played at different types of markets. Anyway, so yeah, what do we do with the two-step estimators? Well, I think we are using numerical derivatives. I think it doesn't really matter. It's pretty simple to do a logit, right? It's globally concave likelihood function, so don't worry about that. And we're using the CCPs as we're getting those from frequency estimators, and then in fact, all the estimators we're going to initialize with these two-step estimators. Okay, so even MPAC, we will get starting values for the structural parameters and also starting values for the conditional choice probabilities based on predictions from these CCP two-step estimators. And then we are considering two versions of these sequential estimation methods. We talked about NPL that Victor went through, and then there's also something called EPL. It's efficient pseudo likelihood. Okay, it turns out, so I haven't went through that here, but there's a very nice paper by Blarians and Schjerning and Blevins, and we're going to put that in the box. That doesn't really rely in the same way on the contraction properties of this NPL operator, because it's essentially based on Newton's method instead. So the successive approximations is less, well, it's not doing that, so it's not going to be fragile to the same sort of instability issues that you'll see with NPL. So we're going to compare with that. And then for MPAC, there's some implementation details, and then we have these two different versions of MPAC, the one with one constraint, we're using the Hartz-Miller version, then the one with the two constraints that Estenla and Su did. Okay, and again, starting values for the using the two-step estimator. So for now, we're just going to look at estimating one single parameter here. Okay, so we have like 1,000 markets in five time periods. Okay. So we choose the parameters so we have some coverage of the state space and not everything becomes totally degenerate. So here are the results for the simple case. Everything works. Okay, let's just go through them one by one. So here's the true value of a parameter. supposed to be 3.5. That, that pretty much nails it, right? And so here's a bias, and this is a Monte Carlo standard deviation. Okay, so I mean, all of this over here, well, this is MPAC, right? 2 versions, and NRLS. This is maximum likelihood. So we expect, I guess, the standard errors should be smaller, and they are. Okay. So and so that's a simple case. Now, what are we computing here?
This case should the NPL also be controlled by slideless middle? As because you start after final number of observations. It shouldn't be full conversion.
That's a good point. And
or maybe it's because you stop prematurely. Yes, maybe you're
does it does say that it converges all the time. Okay. Yeah, I guess maybe these numbers are pretty small, right? And they are getting, well, they're pretty, EPL is doing exactly the same, right? Yeah, I don't have a good answer. See what we're computing here is the log, the difference in the log likelihood for a given Monte Carlo sample. We calculate the difference in the log likelihood to the best one. Okay, so you do like, it's the same sample for all the different estimators. And then we compute the likelihood for all the different estimators. And then we take the one that's the best, and then we subtract that for all of them. So that's a shortfall. So if you have a 0, well, you have a high likelihood you reach the top. Okay, and that's the case everywhere. Okay, so this is, I would say, it's still a really small difference to NPL. I don't have a good answer. Maybe it's numerical noise. Okay, but they are fairly equivalent, I would say. Okay, and so here we also compare. We compute the Kuhlbach-Leibler divergence and also the maximum absolute difference between the true conditional choice probabilities and the implied model ones at the estimated parameters. And we also check if these first order the best response functions, they actually are satisfied. This best response mapping is if it is a fixed point, if it is an equilibrium, both in terms of the choice probabilities and in terms of the choice specific value functions. Okay, I'll get to you. Okay, and you see for all of these, that kind of in all of these cases, they're essentially satisfying the constraints. Okay, now questions. Yes.
This estimates for the point estimate from one parameter, right?
Yeah, just one parameter.
What's the K divergence? As far as I know, K divergence is to compare two distributions.
Yeah, and the two distributions here is governed by the conditional choice probabilities of the data generating process that's at the true parameters, and then the conditional choice probabilities implied by the model at the selected equilibrium at the estimated parameters. Okay, so this is like you get two vectors of conditional choice probabilities, and you can calculate the the true ones. That's the one generating the data, and then you have the predicted ones, the one from the estimated model, and you can compare. That's the difference. That's the KL divergence here, and then you have also just the maximal absolute difference between these two vectors. If you think that's more intuitive. That's what's printed down here. Essentially, that's giving a description of how well is the model actually in finding the right equilibrium, right? Estimating the right equilibrium. These down here tells something about, are the equilibrium constraints satisfied at the estimated parameters? And that's going to be the satisfied almost by construction with MPEG, because if it's not satisfied, we just say it's not converged. Okay, so that's one of those constraints we're going to impose while estimating. NRLS, well, it's solving the model, so we would have had a bug. It would be a poor algorithm if it didn't satisfy the constraints. Just one thing. But the two-step estimators, they're not. If that was your question? Okay. They're not satisfying the constraints. In other words, they might do that in the limit as you get enough data, because, this data is generated from the model, then you will, with your non-parametric frequency estimator, you would, in the end, as a number of observations go to infinity, you would estimate the conditional choice probabilities without any bias, and you put them in, and they're going to satisfy this constraint. So this number would go down as you get more and more data. But you can see here, it's really not imposing the entire structure for the model, because it's not requiring that these estimated CCPs are in fact in line with the predicted CCPs, which is what like Akira, Kabira, and Mira wanted to do, right? They wanted to kind of improve on that and make that restriction being satisfied. And this is also what happens both for NPL and for this recursive updating with the EPL that's using the Newton's method instead. Okay, question. Yeah, well, it's 2 steps. It's much, much faster. We don't have any computer times right here. We will have more Monte Carlos, okay? But it turns out that you scale up the problem, actually this impact becomes really, really, really slow. And then, yeah, anyway.
Because the implementation is not, the best possible for most of the estimators. We worked on trying to be efficient with the NRLS, and the question is it tractable or not? Of course, everything else is fast. And 2-step is the fast. If I may, about the Kyle divergence, a little notice that what is equilibrium? You run a Monte Carlo, you converge to theta, and there's an equilibrium that is selected, which is most likely. Is that the one that generated the data or not? How do you even answer that question? So all you have is a collection of choice probabilities on the state space. That's all, right? That's what you can calculate given the estimates and the equilibrium selection. And so it's actually not a trivial question to say whether you identified an equilibrium or you did not, because as you move the theta parameter, equilibria change, the number of equilibria may change. Maybe you didn't pinpoint the theta parameter accurately enough, and then there's like no scope to talk about whether you identified the equilibrium that generated the theta. And so the Kyle divergence metric here, that's actually a divergence to the distribution of all possible trajectories placed under that are possible to be placed under the data generating equilibrium versus the one that we identified.
Yeah. So it's doing a little bit more than just comparing CCPs, but it's the implication of all the CCPs and transitions.
It's actually solving the fixed point problem to calculate this because we want the distribution of over trajectories given the choice probabilities in points of the state space.
Okay, so I think it's fair to say that equilibrium conditions are satisfied for all these methods that try to come as close to maximum likelihood as possible. So that you got all zeros everywhere. It kind of converges most of the time. MPEG has one situation where it doesn't work. Probably we could make it work. And then NPL and EPL, they are approaching MLE up to epsilon. Okay, up to epsilon. We'll take a look at that. Okay, so now we move to the case of just a little bit multiplicity. Okay, so here's a number of equilibria at the true parameters. Okay, so there's only 3. I mean, we could have situations with 192 million equilibria, like you've seen, but we'll start simple. Okay, so just 3 equilibria. See how is this affecting the different estimators? Okay, there's still going to be one equilibrium in the data, and the equilibrium that we take out of those 3 is a stable equilibrium. Okay. MPEG convergence. Already here, with only 3 equilibria, seems like it's not converging every time. And when it converges, look at these differences in the short likelihood short. It's shortfall. It's significant, right? I mean, this is the. I mean, these are big values. You know, what is the critical value in the chi-square? It's probably 3.8 or something, right? So this is like this is a big difference. And actually, there should be no difference because there's no parameters that are different except for I don't know well, there's the equilibrium selection parameter anyway. So, but what does this suggest? Well, maybe the equilibrium was wrong. No, this is right. All the equilibrium constraints are satisfied. So we have maximized the likelihood function subject to the equilibrium constraints. In both of these situations, equilibrium constraints are satisfied. You look at your optimizer, it says I found a maximum, and then you go. You start working on your paper and do the counterfactuals. The problem is, well, it's not the equilibrium that generated the data that we found. It's some other equilibrium, and it's another set of structural parameters that gave a much lower likelihood. So it's a problem with finding the maximum of the likelihood function. Okay. Do we have a picture of that? Yes. Exactly. That's why it's not 0. But these constraints here, they are satisfied. So the KL divergence and also this more easy to, I don't know, it's easier to interpret, but this absolute difference between the conditional choice probabilities is different, right? It's different over the state space.
So in some ways, the state space, the choice probability is all quite
Yeah.
different.
Yeah.
Would it make sense to actually report the estimated numbers for the estimated equilibrium? So maybe before the number of times the estimator gets the right equilibrium.
Well, we don't know what is right. Yeah, it's Kyle divergence. You want the distribution of Kyle divergence.
Yeah, I guess for them, well, yeah, that's true. Them you don't even get an estimate of the.
This is my co-author taking over. Okay.
Well, the question is 7.499 significantly different from 7.5 to get a different?
But we generated things, you must know which equilibrium that. No, but then we're not sure.
Yeah.
How are you determining the equilibrium?
Well, like I was saying, so the equilibrium is a collection of choice probabilities over the state space. Oh, we solve the model, we generate the data from a particular equilibrium. The one that, you know, reduces the distribution over the path that we measured the KL divergence. I can give you a big set, you know.
You're not.
We know what equilibrium was played in the data. It's just once we've estimated the model, we get out like a bunch of different CCPs. It's not clear how to map that to the.
Well,
we're picking different ones just to illustrate the performance of the estimators under different situations. Yeah, so we're gonna, okay, so this is just an equilibrium where we have picked this only three equilibria at the true parameters, and then we pick one of them, and this one is a stable equilibrium. Okay, we're picking a stable equilibrium because all these iterative algorithms like EPL and NPL, they're gonna have a hard time finding that. Okay, so we're taking that.
Yeah, so
yeah.
If you're talking about the properties, yeah, that's what we control.
Do you know if it's identical?
I think we do.
You mean if the equilibrium selection is identified?
Let's look at the picture.
Yes.
I guess potentially what you could do was to I'd see whether you found the equilibrium result to compare and see the data generating, or so choose the data generating equilibrium, evaluate the CCPs in your in the maximum likelihood estimator, then compare that with, will that work? Yeah.
So the
That-
way,
I think that
the way that now, the way that we now are trying to say whether we are at the right equilibrium or not is to calculate the chiral divergence over the set of all possible trajectories that correspond to a particular equilibrium, given the choice probabilities and the transition group. And that's a fixed point problem, essentially, to calculate this, this measure. But yeah, in a simple sense, you can also just take the absolute difference between the choice probability from the state space, right? See whether the choice probability is there. And in the next slide, you will see it more.
Okay, wait a second. I just want to conclude here and then we go on, okay? So MPEG kind of, finds local maxima, okay? I hope we can agree on that. And then even though the equilibrium conditions are satisfied, it just starts to converge to wrong equilibria. And you can also see that from this KL divergence. Let's look at this graph. I think it makes it very, very clear what's going on. Okay, so first of all, let me just say what is here, right? This is just a likelihood function conditional on each of the different equilibria. Remember we saw this graph with the cliff in the first first lecture. There I only showed the red graph, which is like the upper envelope of these equilibrium specific likelihoods. Okay? Here there's no cliffs. It's just there's a discontinuity, but we have discontinuous likelihoods somewhere. Here's the different estimators located. So you got this is a one-step NPL, and then what do we have? This is NPL. This is going fairly well, okay, but still a little bit off. And then, oh my God, what do you have down here? This is MPEG P, okay? So it did find actually the maximum of an equilibrium-specific likelihood. Okay, so that's why I get back from my optimizer, oh, this looks fine, okay? Gradients are equal to 0, and it's on the likelihood function, so it means all those constraints they are actually satisfied. Okay, so Bellman equations hold, and the players are playing mutual best responses, just selecting a wrong equilibrium. Each of these lines corresponds to a different equilibrium. Here's another MPEG. Okay, it's out there in the woods. Okay, and this is just for one sample. Okay, of course, this picture changes every time you simulate a new data set. Okay. Questions? Yes. Each line corresponds to an equilibrium. That's right. Yeah, that's right. Each line here corresponds to an equilibrium. You can say, well, okay, over here for this low level of the parameters, it's only one equilibrium. Okay, so it's kind of trivial to say this is the first equilibrium. How do we connect the dots here? Well, that's using that KL divergence. So we're essentially using this KL divergence to say, well, in some sense, we vary the parameter. We saw the model again and again create all these different likelihoods conditional on the different equilibria that we find. Okay, but that just gives a bunch of dots. Okay, now we want to make a graph and make them connected. Okay, so we use this KL divergence to measure the distance between different equilibria, and somehow we connect to the closest one. So we say that those are on the same line, are the same type of equilibrium. A little bit like Victor was talking about in the beginning of the week.
Victor drew equilibrium correspondence on Tuesday on the board and talked about types, classes of equilibrium. That's pretty much what you're looking at now, computed for a particular game or for a particular example.
Yeah. But for given value of the parameters, for example, here, you see there's many likelihoods. So that's because there's many different equilibria. Okay. Over here, there's only one. And so when I say that MPEG finds the maximum of an equilibrium-specific likelihood, it's like this likelihood function that is specific to that type of equilibrium. Yeah.
On the identification of the equilibrium selection, it's like if different equilibrium generate different choice probabilities, then like the likelihood functions that actually try to pick one are actually going to pick the correct equilibrium. Okay.
Yeah. Of course, it's more tricky now. We have one more parameter, so there's more flexibility in the model, and but actually, this parameter, this equilibrium selection parameter has a finite support, so it converges actually very quickly compared to if you had a continuous parameter. Yeah, Dennis knows more about that. Okay, so what more? So okay, so here's just for the sake of illustration an unstable equilibrium, and now you can see these sequential estimators, non-surprisingly, does not really do a good job anymore, right? So they're converging to something that's not maximizing the likelihood. It's not even satisfying the constraints. It's very far, but it is satisfying the constraints. Yeah, so it might converge to a wrong equilibrium. So you initialize it with something that's given from the data, but then you start to iterate, and that iteration procedure leads you to a new prediction of conditional choice probabilities and new parameter estimates. And apparently that's not very close to the data in terms of that KL divergence, or just the maximum absolute deviation from the true ones over the state space. So NPL fails to converge, and EPL still performs quite well. And we were actually really surprised about how robust this is. And I think this is because they are not relying on that sequential successive approximation on this NPL mapping, but is using Newton's method. So successive approximation only really works if you have a contraction mapping. So it's not relying on that. Okay. I would say Victor and what is the first name of his co-author, Marco? Well, they have another paper. Okay, I'm sure Marco. Okay, they have another paper where they have. Victor was talking about that earlier, how they will use this gradient-based method with the spectral algorithm, and that does not rely on the contraction mapping properties either. And it has some computational advantages, so that's going to perform much better than this successive approximation application of NPL. So, but we haven't done that. Okay, so what is there to say about this? It's a similar picture, yes. Again, NPL here in the woods. That's a corner solution, right? MPEG, yeah. MPEG, yeah. And NPL here is not on the likelihood function. Okay, it's okay. Now we have more parameters. Okay, and this parameter, this likelihood, we change parameters a little bit, so we have now 9 parameters or nine equilibria. We're still playing one in the data, and we chose an equilibrium that would, or a set of parameters that would create these cliffs you saw in the beginning, like discontinuous likelihoods. What happens is that sometimes these equilibria just disappear out of the blue, and then the likelihood function becomes discontinuous. Of course, this is going to be even harder to find the maximum likelihood estimator, also with these recursive or sequential estimators. Okay, and you can kind of get trapped, as you can see here. Both NPL and EPL get trapped on the wrong equilibrium. And how do you get away from that? Because it is a solution to the NPL fixed points. So, once you got into that trap, you're not going to get out again. So let's look at the results here. So you have the similar convergence issues, but this is the kind of stuff that also destroys some of the numerical properties of both NPL and EPL and also MPEG. Okay, so we have all this log likelihood shortfall. Of course, NRLS works all the time. Yes. More multiplicity. Well, that's 5 more minutes. Okay, more multiplicity. Well, we didn't go quite yet to the 192 million equilibria case, but here's one where there's at least a couple of thousands equilibria. And you might ask, well, can RLS even find those, find the maximum likelihood estimator in that case? So here we have 2,455 equilibria, still one equilibrium plate in the data. It takes 10 minutes to compute all those equilibria at the true parameters. But you don't even need to do that to implement the maximum likelihood estimator, just because of what Fedor told you, right? That we don't need to explore all these different, very, very unlikely equilibria because they're going to be knocked out by that bounding functions, potentially extended with this non-parametric likelihood. So the data just knocks out a lot of equilibria that is just not very likely. So if you look at the computer time to do that, NRLS in this case, where just solving the model takes 10 minutes, we do it in 4.7 seconds. Okay, so I mean what?
Estimation.
Yeah, we do estimation in 4.7. Okay, I mean, imagine that you did the full enumeration for all your trial values of the structural parameters. You do the brute force implementation of the nested fixed point algorithm. Well, then for every time you want to evaluate the likelihood, you would have to compute all the equilibria, wait for 10 minutes, and then you get your likelihood correspondence. You take the max, that's your likelihood, and then you change parameters again, and then another 10 minutes. Okay, that's not what we're doing. Right? We're doing the NRLS. Okay, and that only takes 4.7 seconds to estimate the whole loop. Okay, so searching over both the equilibrium selection and the structural parameters. Okay, and here's the true value. So it's yeah, that's reasonable close. Here's a bias. It's doing what it should. It's the highest likelihood. KL divergence is pretty low, and the yeah, sometimes it's and its equilibrium constraints are satisfied, and it converges all the time. EPL and NPL sometimes have problems, and that's expected, right? You can fall into all these traps. Now they are like, before there was like only 3 traps or 9 traps because it was 9 equilibria, right? Now there's 2,400 traps to fall into, right? So it's really hard to do. Of course, the two-step estimators, you just need more data if you want to do that. That's still working. So is there more to say? Well, we are trying to do this now with multiplicity of equilibria in the data as well, okay? What do you say?
Just follow the lecture, Stefan.
Yeah, we'll follow Stefan. Okay, so we'll try to use these methods to, first you estimate the conditional choice probabilities. You group these different markets into some groups based on things based on these clustering methods, and then you can apply NRLS to construct the likelihoods for each of these different groups to allow the different equilibria to be played at different markets. And so we haven't done that yet, but we definitely think it's feasible and it's fun. Do we have more to say? No, I think so. I'm just going to stop here. Yeah.